There is a star called Beta Pictoris. It sits 63 light-years from Earth, in the southern constellation of the same name, and it is one of the most studied stars in the entire Milky Way. Astronomers have been photographing it, analyzing it, and cataloging its planets for decades. It is, in the language of planetary science, a known system, not a mystery, not unexplored territory. A star with a documented history of scientific attention stretching back more than 40 years. 2 planets had already been confirmed there. Their orbits had been calculated. Their masses had been estimated. The system was considered understood, in the sense that you can understand something you have been watching for that long. And then, in July of 2026, while researchers were using the James Webb Space Telescope to study the atmosphere of one of the known planets, something appeared in the data that should not have been there. An unexpected bright source in the imaging. A chemical fingerprint in the spectrograph that did not belong to any object anyone was looking for. It was a third planet, a giant world that had been in every observation of the Beta Pictoris system for over a decade, hiding in images collected by ground-based telescopes across 11 years of observations, appearing in data that dozens of research teams had analyzed. Detected by nobody because nobody was looking at the right part of the light in the right way. It was not hiding behind anything. It was not in a region too faint to photograph. It was in the most literal sense, hiding in plain sight. In one image, it was barely visible against the glow of the planet that everyone was actually trying to study, a world that had been in the data for 11 years, overlooked, until Webb accidentally revealed it while looking for something else entirely. If one of the most studied planetary systems in the galaxy could hide a planet for over a decade, it raises a question that the recent history of exoplanet discovery has been forcing scientists to confront with increasing urgency. How many more worlds are hiding in data we already have, around stars we already consider well understood, waiting for an instrument or a technique or an algorithm that was not looking for them to accidentally reveal them? The answer that has emerged from 2025 and 2026 is that the number is considerably larger than anyone expected. Start with the star closest to our Sun that we know hosts planets. Barnard's star sits just 6 light-years from Earth, making it the second closest star system to us after the Alpha Centauri system. It was the first star outside our solar system for which astronomers attempted to detect planetary companions, in observations beginning in the 1930s. For most of the 20th century, it was considered one of the most carefully watched stars in the sky. And in 2025, 4 planets were confirmed orbiting it, not discovered in 2025 confirmed. 4 worlds that had not been part of any previous accepted planetary inventory of Barnard's star, despite nearly a century of observation. All 4 are in a size category that does not exist in our solar system. Smaller than Earth and Venus, but larger than Mars. A class of world that theory predicted should be common but that our own neighborhood never showed us. The University of Cambridge research team that published the confirmation in June of 2026 analyzed the chemical composition of the star itself to understand what the planets are made of. Their conclusion was that these worlds are far stranger and more hostile than expected, with compositions and internal structures that the standard models of planet formation in this size range do not easily account for. For alien worlds, 6 light-years away, hidden in a century of observation, until the instruments and analysis techniques finally caught up with what was there. Now go to July 21, 2026. Astronomers announced something that would have been considered one of the most significant findings in the history of exoplanet science if it had arrived in any other week: a confirmed atmosphere around a rocky planet in another star's habitable zone. The planet is LHS 1140b, orbiting a red dwarf star approximately 48 light-years from Earth. Previous observations had suggested an atmosphere might be present. The July 2026 James Webb data made it definitive. Researchers confirmed that LHS 1140b has an atmosphere, not a hydrogen-rich remnant of its formation, a secondary atmosphere, produced after the planet's birth, the kind of atmosphere that on Earth was shaped partly by geological processes and partly by biology. The lead researchers described the finding as extraordinary. 1140b was already considered one of the most promising, potentially habitable worlds known to science. The confirmation of its atmosphere moved it from promising to confirmed candidate in a single announcement, and the characterization of what that atmosphere contains is the next target for Webb's instruments. This is a world that was not hiding from us. We knew it existed. What was hiding was its atmosphere, waiting for Webb's infrared sensitivity to resolve it clearly enough for a definitive conclusion. Now here is one that was hiding specifically because Einstein predicted it, and no one thought to look until July of 2026. A planet designated Gaia to 3 Bra b was confirmed through a technique called gravitational microlensing, using data from NASA's TESS mission that was designed to find planets through a completely different method. Microlensing works by detecting the brief brightening of a background star when a massive object passes in front of it, bending the background star's light like a gravitational lens. Einstein predicted this effect more than a century ago as a consequence of general relativity. The planet is located approximately 40,000 light-years from Earth. far outside the range of any conventional exoplanet detection method. It was hiding not because it was small or faint, but because the only way to see it was to watch it bend light from a background star during a fleeting, unrepeatable event. TESS was not designed to look for it. The microlensing signal appeared in test data anyway, and researchers recognized what they were looking at only after the fact. A world 40,000 light-years away, revealed by a gravitational effect that general relativity predicted before anyone knew planets beyond our solar system existed. In June of 2026, a mystery that had persisted for more than a decade was solved. Astronomers had known about a world 57 light-years away that they called the Pink Planet. Its color was unusual. Its mass was unusual. Its orbit was unusual. For over 10 years, it resisted clean explanation within the standard models of planet formation. In June of 2026, James Webb's observations finally revealed why. The planet's atmosphere contains compounds and cloud structures that produce its characteristic color through a combination of chemistry that no previous telescope had the sensitivity to resolve. The solution was not exotic. It was invisible until the instrumentation caught up with the planet. For 10 years, this world sat in the catalog as a documented anomaly. It was hiding not in the sense that it was concealed, but in the sense that the physics explaining it was beyond what anyone could see. And then there are the cotton candy planets. In May of 2026, astronomers confirmed 2 rare superpuff planets, worlds with densities so low that researchers describe them as lighter than cotton candy. These are not small planets. They are roughly Neptune-sized in diameter. But their masses are so low relative to their volumes that the densest material known to science would not be able to constitute them in any arrangement that makes physical sense under conventional planet formation models. They have been hiding, not in the observational data but in the theoretical framework. Standard models of planetary structure produced no category for them. They exist at the outer boundary of what current physics says a planet can be, in a region of the parameter space that theorists had not considered worth modeling because it seemed too extreme to be physical. The confirmation of 2 of them in a single year forces planet formation theory to expand its range of acceptable outcomes. In May of 2026, Raven, an AI system developed at the University of Warwick and applied to NASA test mission data, confirmed more than 100 exoplanets in a single published study, including 31 newly identified worlds. The system scans data from millions of stars, identifies the tiny dips in starlight caused by transiting planets, filters out false signals using AI trained on realistic simulations, and statistically confirms the strongest candidates. What Raven also does, and this is the detail most coverage missed, is evaluate which types of planets are easier or harder to detect using the transit method, allowing researchers to correct for hidden biases in the existing catalog. The implication is that the current inventory of confirmed exoplanets is not a random sample of what is out there. It is a biased sample, weighted toward planets that the transit method detects efficiently, which means smaller, shorter, denser worlds. The catalog of 6,000-plus confirmed exoplanets that NASA reached as a milestone in September of 2025 does not represent 6,000 random draws from the universe's actual planetary population. It represents 6,000 draws from the subset that our current techniques happen to detect most easily. The planets hiding in the remaining space of that distribution are not hypothetical. They are there. They are just waiting for techniques like microlensing, direct imaging, atmospheric chemistry, fingerprinting, and AI-driven data analysis to pull them out of the noise. In December of 2025, a study using the Subaru Telescope in Hawaii and ultra-precise space data uncovered a massive hidden planet and a rare failed star, an object between a planet and a star in mass called a brown dwarf, in a system that previous surveys had categorized as containing nothing notable. The object was lurking in archival data, detectable only when ground-based imaging was combined with space-based astrometry at a precision that became available only recently. It had been there for every year of previous observation. The instruments that could see it simply did not exist until now. In September of 2025, a trans-Neptunian object, designated 2017 of 201, was identified at the edge of our own solar system, with an orbit spanning 25,000 years and a size that may qualify it for dwarf planet status. It had been in survey data since 2017, identifying it as significant required updated analysis techniques applied to existing data 8 years after the data was collected. The pattern that emerges from all of these cases is not a story about failures of astronomy. The history of exoplanet discovery has been extraordinarily successful by any reasonable measure. The pattern is a story about limits of technique. Every detection method has a range of planets it finds efficiently, and a range it misses entirely. The transit method misses planets with long orbital periods and large orbital inclinations. Direct imaging misses planets too close to their stars to separate from the glare. Velocity measurements miss planets around young, active stars whose own variability drowns out the planetary signal. Microlensing finds planets that nothing else can see, but only during unrepeatable events. And the chemical fingerprinting method that found Beta Pictoris d was not developed as a planet detection technique. At all, it was developed to study atmospheres, and a planet hiding in 11 years of archival images appeared as a side effect. NASA's Roman Space Telescope, expected to launch in the coming years, has been designed to find approximately 100,000 exoplanets, primarily through microlensing, in a survey designed specifically to probe the region of parameter space that all previous methods have left incompletely mapped. 100,000 worlds, most of them currently hiding in the dark between stars in the inner galaxy, waiting for a telescope whose field of view and sensitivity are matched to the scale of the search. The 6,000 planets we have confirmed are the ones that happen to be visible to the techniques we had. The universe is not withholding the rest. We simply have not yet built the eyes to see them.